Well, good afternoon. Greetings, gentle readers. Today is June 7th, 2024, and it is Friday evening. So today, in Moment in Motion, what I hope to do was talk a bit about the mechanics of motion, the theory of a mathematical motion and a model of mathematical motion. That the geometry is motion is one of the themes in these talks, and what it means to entail is that perspective and projection come together to make it so that geometry arises in this sense of the axiomless natural deduction as sort of from first principles, whatever they may be, just so as vacuously from the ponderance of breaking down a whole into parts and finally into points, or assembling things that make proportion and form a line or the spiral space-filling curve, that it so arises that in Euclid's geometry with our classical constructions that make it so that it creates objects of the elements of Euclid's elements of geometry, points and lines and ... make it so that we have this square of opposition of the points and spaces, a point, and then in any number of dimensions a space, and the greater space of all these real values, that it so works out that that's kind of how it is, that axiomless natural deduction arrives at this moment in motion as points in space. So the theme and the context here has been a lot about trying to figure out that our laws of motion have rest and motion as these two fundamental states. So we have states and change. And then anything that stays it has state as static, and anything that changes is dynamics. And so it's the same root word for dynamis and dunamis, where potential is the potentiality of something to happen, and that unchanged in its surrounds and situation it will. That according to this theory of sum of history, sum of potentials, they just add up to the tendencies and propensities of things. So dunamis is that word, and then dynamis is kind of the same word, but then it also affects to relay the situations of conditions that are quite variable, whether they're energetic or whether they're monumental, or whether they make changes in things, that they're instrumental, say. So these are the kinds of things then that trying to figure out more of this model of mathematical motion, that our mathematical model of motion basically is about the linear, and that something that's at rest it has 0 meters per second, and something that is in motion has its velocity meters per second in our standard units. That according to our theory of space and time, we have 3 space dimensions. It's got width, height, and breadth, and that's how it is, and all such matters of the linear that way, and then all such matters of the rotational are basically that they're free rotational settings, and so far as regards to the space frames and frame spaces of general relativity, framing the Lorentzian as the Lorentzian and Fitzgeraldian, and the Lorentzian and Einsteinian for the general relativity and special relativity, and how Einstein broke that apart a little bit in his parting gift of Out of My Later Years is to define the spatial, as you usually spell it, S-P-A-T-I-A-L, spatial, and then another word, spatial, S-P-A-C-I-A-L. So basically his special relativity is spatial, and the terms he applies and puts to that are like so, and then the general relativity in usual matters of the bodies themselves are spatial. And so spatial is spelled as S-P-A-T-I-A-L, spatial, and spatial is a different word that Einstein kind of introduced to help, on the one hand, disambiguate the two, and the other hand, in a slight enough manner that otherwise it would gloss over in the reading as not changing otherwise people's perceptions that they may have of it, which is when special relativity is set in front of general relativity, kind of in the order of their discovery or their formulation, as it were, instead of the other way around, which they can be kind of derived either way, these bridge results, but that it's something pretty particular about Einstein's theory of relativity, he calls it not just general relativity, the theory, and special relativity, but his overall together theory of relativity that Einstein says SR is local and it's spatial, and then there's all such matters of the space and space contraction make these frame spaces and space frames called Raman and Raman, German words for frame spaces and space frames. And in this manner, motion was something that he was trying to figure out, and especially in the overall course of the things. So here, that's kind of given as the background. So that's kind of the theory. That is the theory. It's sort of modern, It's sort of insofar as that's the way things are. That's the way things are. And so insofar as that's the way things are, then classically is that in the limit it's classical, which is basically where all these other factors of dynamics fall out of space contraction, right, basically. And yet then we're left again to redefine, to make a definition for all the infinitely many higher orders of acceleration. Because linear motion then is adjusted as by acceleration. And force, the quantity, the physical quantity, is defined by that a given mass will be accelerated by a given force in a proportional relation. F equals ma. That to accelerate a given body of a given mass, it takes a given force. And it's only exactly insofar as that application of force where it exists and lives is a constant. Because if it changes, it has to change, and 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 so on and so on. One of the authors that I enjoyed reading, and especially when I read his description of special relativity, it was the most reasonable way I felt like at the time when I'd felt that I'd comprehended that light speed is a constant, and basically the L principle or light principle of special relativity was PCH Davies or Paul Davies. And so he's a Englishman, I suppose, and he's written a bunch of books in the 80s. And so and he's kind of he frames things mostly in the scientific. And so in this book, The Superforce, it's from the 80s, and so it has this really great description about some of these things that we talk about here. And one of them was about the, and there's lots of concepts to be considered in something like that, whereas he's trying to just come to terms with continuum mechanics at all. But one thing he said was that the square of the force was as about the cube of the distance, the part of the elliptics to explain the orbits and stuff like that. And then there was another part of the expressions that he had made so sensible, where in these concepts of the infinitely many higher orders of acceleration, that there's the linear force and its application. And so that's just classical and a constant. Oh, and what he discussed was this. You may be familiar with the particular character of the exponential function. And especially in the realm of real analysis and calculus, the differential, that the exponential function is its own antiderivative and its own prederivative or integral. So it's its own integral and it's its own derivative. So what that means is that any point on the curve of the exponential function, the e to the x, the natural logarithm e to the x, that if that's the function f, then df dx equals e to the x. And the integral of that equals e to the x plus a constant, say, or c, or this or that. So that's just helping to relay that all the infinitely many orders of that kind of carry it forward. And so what he mentioned was that sine, when you take the derivative of sine, then you get cosine, and you take the derivative again, you get negative sine, and then you get negative cosine, then sine again, or something like that. There's a cyclical tendency around these formulas that, according to the operator calculus, it forms again these groups and stuff that come back around. And so when we get to considering things about like the infinitely many higher orders of acceleration, and each one of those having its inputs, then that was just kind of, I related that to this, because when we're talking about the differential equations and those that have this property of also resulting that they're invariant, unchanging, under the application of otherwise these laws that decimate the function, meaning they bring it down to zero, or they explode the function, which means they just take it away up into all the higher orders, that instead it keeps it constant. These kinds of invariants are what we're looking for to implement these things we've been talking about, called the stop derivative, the walk integral, the pause integral, and the run derivative. These being the ideas of ways to frame that for meeting and parting and starting and stopping, that there are differences and reasons why, and it helps to explain what's in this theory of sum of potentials, sum of histories, either way, and makes for orbits that instead of kind of classical motion as being just linear and an impulse is to proceed, which it is the limit and the sum, and it results being as well a potential that's evoked, the classical force that is really built up of all these other parts about it. And then as these things move along and they move in the system, the frame and the space and the frame, they move in terms of what energy is exchanged and contained, all following all the laws of physics, all following all the laws of motion that we have, filling out how to define the way those are framed in their perspectives and according to these projections from the original coordinates outward in the relativistic setting, or kind of generally on their continuous manifold on their way in their orbits. That this is a way to look at these things to help make it so that we'll at least have a mathematical model of motion as some kind of model of mathematical motion. So that's kind of what I've been trying to figure out a little bit since I started talking here. Oh, it's a nice day. It's June, so summer would start at the solstice, which is usually at the 21st, or what is it, the 23rd? What is it different? Or there's that, it's after Memorial Day, so it's summertime. And it's about 80 degrees or so Fahrenheit, I suppose, if one were to get a thermometer and according to the various technologies used to assemble such a thing and how it may so be. Well, all right then. What I've done is I found some books, so I'll hope to find some inspiration from some of these books, and we'll get an idea of what they're talking about and what they may have brought to the discussion. Well, the first one here, these are some books from the 1960s and 70s. This is Planetary Electrodynamics. And so what it intends to tell is that Gordon Breach Scientific Publishers, from the proceedings of the Fourth International Conference on the Universal Aspects of Atmospheric Electricity, which kind of indicates the ionosphere, that the Earth is surrounded by these layers of bands of atmosphere and charged particles, or plasma fields, or fields, magnetic fields. So you kind of got like the stratosphere is 30,000 feet. Above that is the ionosphere, anything that's outside that, or as of the more radical ions, say. So this is sponsored by the Joint Committee on Atmospheric Electricity of IAMAP and IAGA of the Geophysical Union and the Science Council of Japan, out of the ONR and Avco Space System Division by Cornelius and Hughes. So I thought this was pretty interesting. They talk about thunderclouds, space electricity, monitoring of global thunderstorm activity, and fair weather electricity. And I don't really expect to find so much about motion in this, or these classical laws, or trying to figure out this. This will be more of kind of a macroscopic approach, I imagine. But it does have some interesting sections when I was just leafing through it, helping to explain some of the features that get involved out past the terrestrial frame, because the Lorentzian fields make for the Fitzgeraldian, which is kind of like where space contraction lives and is kinetic. And then they have for the Maxwellian, which is anything to do with the electromagnetism, kind of all Lorentzian, which is Galilean linearly, meaning it's like it's just like linear motion everything is linear that moves. And then we have kind of like the Lorentzian is for Einstein is for special relativity, which was just mentioned. He's like, and this is a separate special spatial domain for special relativity and light's behavior, because light just moves freely compared to this other stuff that all lives in our tachyonic world, yet in a Galilean world, meaning according to the Galileo's Galilean invariants, which are just like the Lorentzian invariants, except the Lorentzian invariants add a term for time. And also to light. So the Galilean has a space-like and the time-like. The Lorentzian has a space-like, time-like, and the light-like in the differential equation that says all their differentials equal 0 in the invariance, as it were, of that. Or in terms of when that's curved at all, that just means like, well, one of them is flexing. So it's like so. So this had something that was interesting about this, but it's about atmospheric electricity. It doesn't really have so much about atmospheric heat. Tropospheric ionization. So the troposphere, there's these many layers describing the density of air, its usual contents, air speeds, height, usually just according to height, and then its magnetic state and disturbances, and also ionizing radiation of the radionuclear, where it's to be kept in mind that the radionuclear often involves radiation, and it's described as rays, and a lot of times all that's said to be like the electromagnetic spectrum because it has frequency and wavelength, and it kind of is governed by the by Maxwell's equations, but that neither light nor radionuclear energy necessarily has electrical charge at all, that it's tachyonic or bradyonic, and that it is maybe ionizing and radiation, and it is rays, is just to keep in mind that optical light is special and these kinds of things. And that it's all energy in forms, and they exchange and interchange variously in media. So these are the kinds of things. Planetary atmospheric electricity. It's got a portrait of the conference, and here's about 100 fellows, 98 fellows, ladies and gentlemen, mostly in suits. And so in this book, it's kind of got a summary of extremely low frequency noise and Schumann resonances. So that'd be interesting, because Schumann references, Schumann, describe the potential for the energy. When people used to talk about electricity in the air, this was before there was a theory, really. Though the theory of electricity has been around since like Babylonian times, and they had just clay jars with electrodes in them and some like vinegar, and they would make little batteries out of them. Like in the ancient times, electricity kind of had a theory. Vis-a-vis that the word kind of comes from the feeling of electricity in the air when there's lightning to strike, which is a matter of potential and bridging the gap, the air gap of potential from lightning. These days there's so many grounds for lightning that a lot of it just kind of dissipates naturally. But if there wasn't like largely in a lot of different ways, all these different means of code, they call it in the construction code, there would be a lot more lightning. Flash counters, lightning, electrostatic plumes, atmosphere's fair weather electric field, electrode effect, comparison of theory and measurement, analog simulation of global electric currents, model for ball lightning, decaying lightning channels, bead lightning, and ball lightning, lightning discharge, electrohydrodynamic phenomena in the Earth's atmosphere, electrostatic instability in the magnetosphere as a cause for electric fields. So that looks kind of interesting because it involves electrostatics and electrodynamics. Because current flow and electricity it's got a fluid model, and so when you think of a usual circuit, of course, It's just got the electromotive force or voltage. It's just like pressure, and then resistance is just like having it to like go uphill basically, or as a block, a gate for it. It reduces the velocity. Otherwise, what makes current, and current is kind of just measured in the same as velocity. But electrons don't really move around that fast. They just kind of jostle back and forth, and it's the holes that move is in our theory what's called, according in the statistical ensemble, by the theory which computes the thing, is by the Leonard-Wishart potentials of a test charge in a particle, and the according to the potentials, how that charge as a test particle, an infinitesimal or point particle amount, will move as an electron hole through the jostling of these the electrons proper in the nuclear model of it. So there are other models in Leonard-Wishart. I've seen several derivations. I mean, one guy just kind of came up. He's like, look, I made these things that are not Leonard-Wishart, but solve for it. And give some different results in some particular situations that are relevant. He was some kind of electrical engineer designing chips or something. So he just came up with some of these different ways and was like, look, I found this for Leonard-Wishart. And they're different. And that's cool because, at the same time, in every physics university course, Physics 300 or whatever for electricity and magnetism, they instruct this exactly. And it takes a while to get to it. It takes a while to get through it. And at the same time, he's like, well, no, they never heard of this. And so it could be very enriching. That's dope, there's much of the empirical in the electrical engineering, to be sure. Tentative synthesis of electrohydrodynamic phenomena in the Earth's atmosphere. So electrostatic instability. So electrostatic and electrodynamics get into the potential again, and the pregnancy of it kind of is like when the potential gets close to happening, then it kind of broadens the fact that there'll be a gap, that it will arc the gap, where the arc is when the very first spark happens, because as soon as that happens, then it's like full current occurs. So the liquid model is great. It's like you compute this with Ohm and Kirchhoff law. It's just like water flowing around in the circuit. But it's got, instead of this core effect of water, it's got this skin effect of electricity, and it's got these different things going on with phase and polarity, and the resonances. It's all on the outside of that. These changes cascade according to the establishment of this connection around the entire loop, say. Static charge, static discharge, or shock it's usually called, which is the breakdown of capacitance by means of an arc in electricity. So on page 303, and he's got turbulent conductivities, electric fields in space and on the lunar surface. See, that's one thing. Without ground, is like the free cloud of electrical potentials develops around a thing, and so when they ground, then that's like they come back together, and so it's to be figured out how things are done. In the old days, they used to have like electrostatic discharge conditions around a lot of different kinds of equipment. First of all, it's like, this is high voltage, don't open the case. And secondly, it was like, well, it's like you can destroy and fry this tremendous supercomputer by scuffling your feet in the carpet and giving it a zap. Those were the days. Usually the server room is quite secured. 303. Electric field in the ionosphere, a theory of its origin and effect, by Hari K. Sen, Air Force Cambridge Research Laboratories, Bedford, Massachusetts. The anomalously high electron temperature, that I need to learn about, electron temperature, in the lower ionosphere cannot be attributed to photoelectrons. It is shown in this paper that electric fields due to charge separation in the dynamo region provide adequate energy for this purpose. So the dynamo region, the dynamo is the usual idea of the dynamics again. Something starts spinning and it has inertia, and here things are framed instead of momentum to try and frame things in inertia, because momentum is kind of set in this theory to have like be part of the open aspects of eventually conserved, vis-a-vis the inertia is the kind of the real conserved quantity. Because of this, the whole definition of acceleration and the things. That's the thing. So application of the formula for the velocity distribution of electrons in crossed electric and magnetic fields, Sen and Wheeler, 1960, to the observational data gives electric fields perpendicular to the magnetic field of intensity about 20 or 40 volts per kilometer. This is an order of magnitude higher than that obtained in the current dynamo theory. Theory is given an origin of the electric field and charge separation due to neutral wind drag. This theory leads to the right order of magnitude estimate of the dimensions of ionospheric irregularities. Observational evidence. Existence of electric fields in the ionosphere considerably greater in intensity than given by current theories. Spencer and Brace remark the heating observed in the E region can be explained only in part by solar X-rays. Appears to require an additional source such as an electric field. Large discrepancies suggested electric fields. The effect is considerably enhanced in aurorae, and temperatures of 1 to 3,000 kelvins are obtained. Measured electric fields, found auroral electric fields, obtained electric fields, thermal enhancement, estimate of scale. So this is not particularly, unusual, it seems. I mean, it's just dynamics of the Coriolis effect. So if there's a big force on the outside of the Earth with regards to the air, it's the Coriolis effect. And the idea is that if the Earth's spinning around, it's kind of like Einstein's train. It's absolutely still inside the train. Absolutely still. And even when it's moving, because inside everything's moving relatively, that they're at rest with each other. So the idea of Coriolis is as the world spins around, it's why the prevailing wind kind of comes the other way. Like there's any drag at all. It's like, well, there's no drag. That would mean there was some like effect that this air particles were different. But it's observed. So the Coriolis effect is that. And Coriolis goes along with the Compton effect and goes with the Sagnac effect and about Ehrenfest and stuff like that. But Coriolis is, for example, why there could never be a space elevator, because it would just roll out from underneath it. When we think about stuff like, well, how about geosynchronous orbit at 25,000? Why doesn't that suffer Coriolis effect? It's like, well, that's actually far enough away that it's naturally in its orbit to spin around at the same rate. It's not like fixed there. It's flying around at the same rate. That was another one of these formulas that Davies wrote in the first few pages or chapters of this book, the superforce, which is kind of grandiosely named, and then he kind of, hits an end to all of this stuff like the continuum mechanics, but at the same time, he has a lot of like bait for people to, have something to talk about and impress all their scientific friends, because they would know this factoid. Then also he gets into quite the deeper details about like things like the real wave function. He had a great thing that I wanted to quote about, which was a survey in the 80s of after the aspect experiments and what was going on in his world. And he's like, out of this handful of people, and they're eminent people, a couple of them were like, well, we're stuck and staying with the stochastic interpretation because so what? And then the other ones were like, we all eventually got to arrive at some kind of real world wave function here. And he gets also into that the particles as points are just a conceit. They're just kind of theoretical, and they only exist in terms of the events. So following these laws of large numbers and collapse as infinitesimals and individua of continuum mechanics. So that's the way things are. Or were, and 1980s. And today it's the kind of core of the theoretical people kind of still keep up with that, while the outside is still like, this is our coffee table book, this is our linear algebra from high school, you know, without, you know, getting too far afield into the non-standard, or it's just the singular, like the regular singular points of these integral equations of 0, 1, and infinity. Just one, and just a least sort of infinity, just something that's kind of still easy to deal with and figuring stuff out. Dynamo region, estimated scale, atmospheric irregularity, the magnetospheric plasma sheath, the terrestrial magnetic field at the magnetopause, distance about 10 radius Earth from the Earth's center, where radius Earth is Earth's radius, r sub e, acts like a rigid wall to withstand the impact of the solar wind. A plasma sheath a few Debye lengths thick, which is brief, will form at the magnetopause in the same way as at the wall of a laboratory discharge tube. The potential drop, so it's very thin, but it goes around the Earth. Will form at the magnetopause. The potential drop V across the sheath, producing electrical field in the anti-solar direction, is given by Thomson in 1962. It's 3.76. We take the following parameters, the magnetopause, 10 inverse cubic centimeters, T equals 10 to the 5 kelvins. Then the Debye length is about 7 meters. Oh. Huh. Debye is regards to diffraction and wavelengths and stuff. I need to refresh. Maybe that's why I was thinking it was more like microns or something like that. It's one of these things. The other day, there was something in physics. I was reading an article, and it has to do with the neutrinos, because I think that after the infrared catastrophe and electron physics and the great success of spectroscopy in the discrete and particles in the discrete and all these things that have to do with our atomic models and the fundamental physical constants, that's great, and linear and Wheat chart and all this stuff, and it's great. Then for things like beta decay and muon physics and stuff like that, which like, well, it's got to be continuous again at some point. Like we got spectral lines and like the hydrogen line, but sodium's got 3 lines, you know, making this stuff up for why it's continuum mechanics again. It all builds up as it breaks down. It's points and lines and points meeting in the middle of nowhere. That for this idea was that there's Higgs, and so Higgs is supposed like, well, we're gonna figure out the most massive aspect of symmetry when symmetry breaking happens on massive bodies by how many tera electron volts, giga electron volts, tera electron volts that will make it result a particle will be so huge that we say our standard model of particle mechanics as for Pauli and Born and the usual particle statistics, the standard model of particle physics will be done, and we'll call that the Higgs boson, and say that was the greatest thing. And so this was discovered some years ago, and when they discovered it, they got the experiment set up and ran it up, and they're like, well, it's great, and it's like, it's done. It's like, okay, it's done. How does it look? It's like, well, it's kind of like you expect. It's like a ball as big as we figured. It's there. It's like, well, that's fantastic. Can we look at it? It's like, well, I don't really want to show you the chart because you might not interpret it the really way it's intended. It's like, well, what do you mean? It's like, well, it's basically split down the middle. It's a doublet. It's got a divot in the middle. It's like, what does that mean? It's like, well, it's the last standard particle. It's done. It's this last standard particle. It's first non-standard particle. It's like, oh, great. So people have heard of that before. And this was discovered some years ago, and it takes a while to kind of absorb kind of, well, what does it mean? That it's like just that's massy enough that everything is at least strong enough to like hold up to that. Like the energy levels mean everything is so sound, and the firmament and fundament is profound to these energy levels. It's real. But then the whole idea of the neutrino physics is like the neutrinos are tiny massless particles and they fly at super high velocities. So they're this complement altogether, this thing. And then people are thinking, well, like supersymmetry is dead, is the usual refrain, because it was supposed to be show up out here, and they're like, well, we're not quite sure if we're finding that out there. So what they have in the theory these days also is, because the other part of supersymmetry is like, well, when anything moves, it's like just everything fluxes the other way. It's the same thing for this electrical current and this potential and the differences between it and the fluid model and water in the fluid model. It's flux the other way. Light is lux. This fleeting flux is this reciprocal motion, this consequent supersymmetric motion. So the neutrino physics, the idea is kind of like, these are these things. It's like, what are neutrinos? Well, every day from the sun, there come billions of neutrinos, and we can detect a few, maybe. It's like, okay, great. Well, what do? It's like, well, actually, they're kind of flying into the sun. It's like the solar wind is coming this way, and the neutrinos are kind of going the other way. Well, how could that be? Are you really saying there's some kind of this kind of influx? It's like, it might be. And so this little Higgs theory is like, well, it's just more about this Higgs, but this Higgs back in the order of the atom again, and the graviton is the real graviton, and the atom is the real graviton, and this is his own virtual partner, and so it seems to be reasonable, this 0, 1, and infinity type of it. Yeah. And then if there's a neutrino, it's just kind of like slightly negative. It's like, now this is me though, I was like, do you mean the neutrino is kind of like this little Higgs too? I was like, yeah, kind of. So that amused me. And it's a thing. It's mathematical. It exists because 0, 1, and infinity make numbers. So in this theory of some histories and some potentials, that's kind of how it is. So about the magnetopause sheath, and this is kind of like when you think of the ozone layer, and this is a pretty significant thing too. And then you talk about the ozone layer blocking solar radiation from frying everybody, is that this magnetopause is very significant affect the buffer. So it's interesting. And so it's 35 meters thick, he says. But that's for Debye. And so Debye, D-E-B-Y-E, is a scientist, and he has very relevant formulas with respect to diffraction and stuff like that, which help express the reflection and refraction about these kinds of things. Then the sheath electric field. We take the magnetic field, the electric field, swim parameters, the electron-ion collision frequency, the electronic gyrofrequency, the Hall conductivity, the Hall current density, the Hall effect and the quantum Hall effect are big deals, kind of like with the Coriolis, with the aspect type experiments, with Sagnac, with Compton, with anomalous things that are really super classical somehow. Here, Sen is describing that it affects an interaction between the magnetic field that's an envelope about the Earth, with a sheath, which is for its skin effect at the skin of this field. And then he says, talks about the lifetime of the sheet current until it settles down to an ambipolar flow. This is about 19 hours after a magnetic storm, toroidal ring current. The drift velocity is 3 times 10 to the 4 kilometers a second. So 30,000 kilometers a second. And that's about 3 times Earth's escape velocity. And this is another one, is like, they were doing some studies of the drift according to the ether theory and frame dragging and drift. So they're like, well, it doesn't really exist, and it's about 11 kilometers a second as far as we could figure out from this experiment up there. It's like, so that's the region of Earth, right? It's like, well, yeah. It's like, Earth's escape velocity is the same as that? It's like, well, yeah, basically the frame dragging constant is the same both inside and right outside Earth's gravity well, because it's like, well, it's within Earth's gravity well, because that's kind of like, that's the force of gravity, that's the well of gravity right there. But then outside it's like, well, that's kind of the region where it lives. That's like what it occludes around it. Pretty fun. that gets into why the equivalence principle, which is that gravity's force and just plain old acceleration's force are the same, is not really falsifiable under the conditions where it's the same. So it takes a rather extended experiment to help set up any cases illustrating not the equivalence principle. It's the thing. An electric field. Discussions on Sen's paper. So this is interesting. They have some comments. In your Oya says, in your model, you propose the formation of the ion sheath region in front of the Earth towards the Sun. Usually the ion sheath is formed by the magnetic field wall, but in your case, what is the actual mechanism that makes such a wall? He says the magnetic field itself acts as the wall because it shuts out the plasma. The plasma cannot penetrate the magnetic field, so physically it acts as the wall. Oya says, is it required that there be a gradient in the intensity of the magnetic field in front of the magnetosphere towards the Sun direction? A gradient in the intensity of the magnetic. And Sen says, well, it may be. I'm considering as a rough picture. When the magnetic field is pushed back, the magnetic pressure increases until it becomes of the order of kinetic energy of wind and can hold the wind back, the solar wind. The Whipple says, the important length, I believe, is not the Debye length at the magnetospheric sheath, but the electron gyro radius, which has a value on the order of a kilometer, is actually on the average somewhere between the electron and ion gyro radius, which should make it several kilometers, or maybe several tens of kilometers. I think you cannot apply the laboratory discharge theory in this way, but we have to solve the Poisson equation to compute the electric field. And Sen says, the electron and the ion could not stay separately at their respective gyro radii, as this would build up a tremendous electric field. Together they would stay at some mean gyro radius. This situation would apply to the plasma as a whole. Within the plasma, however, there would be a fine structure, a separation between the electron and the ion charges of the order of a Debye length. The electrons in the solar wind are reflected back at the magnetopause and mingling with the oncoming electrons sort of Maxwellize them, thereby creating a temperature and a consequent Debye length. The physical picture is closely analogous to what happens near the wall of a discharge tube. So this is assigning kinetic qualities to electrical particles in the particle model, why it would result in secondary radiation. So we didn't quite get to Chuanxing Liu's University of California Department of Physics electrostatic instability in the magnetosphere as a cause for electric field. He talks about the Van Allen belt. That's what most people have heard about. Is like, well, we'd like to have a space elevator to space, but you'd end up spending several hours in the Van Allen belt, and the radioactivity would be a lethal dose. Inside the plasmapause, the energetic belt is found to be stable. Outside the plasmapause, the ring current belt is found to be unstable when the density gradient at the outer edge exceeds a certain critical value. Components of the electric field, both parallel and perpendicular to the magnetic field line, are associated with the instability. The condition for overstability is derived. The possible relevance of the instabilities to auroral phenomena is discussed. Well, this will be something to read some more later. It's quite interesting because it's about space. And so we only have one really experimental setting for that year. It's called Earth. It's terrestrial, it's pretty cool. What's this then? Source book on the space sciences. Again, this is quite outdated, meaning it's 40 years old. Yet it's first edition, and it's from NASA, printed by D. Van Nostrand. This is by Samuel Gladstone. Talks about, well, this is Melvin Day, the director of the Science and Technology Information Division, National Aeronautics and Space Administration. And so this source book, the space sciences, it gets a lot of stuff like microgravity. And so what I hope to glean from this to discover was the mechanics of motion with regards to these things. And so this chapter 2 is about orbits and trajectories. So that'll be as of interesting things. The elements of an orbit. I'll look at this over a little bit further before kind of getting into it. He talks about all kinds of rockets and power sources and applications in space. technologies of the radio, the solar system, the planets, the asteroids, the comets, meteors, meteorites, and tektites. Origin of tektites. Micrometeoroids. Earth and its environment. Earth's gravitational field, the atmosphere, the chemosphere, the ionosphere. So he's got here ozone, greenhouse, noctilucent clouds, and day glow. The ionosphere, major ionospheric disturbances, interaction of radio frequency waves with the ionosphere, determination of electron densities, the magnetosphere, Earth's radiation belt. The moon, a rock. Lunar radiations. Tektites in the moon. Lunar studies. The terrestrial planets, Mercury, Venus, and Mars. Major planets in Pluto. See, back then, Pluto was still a planet. The origin of Pluto, 762. Now that should be read. Let's see here. The universe. Man in space. Meaning, of course, mankind. Pluto was captured. Another problem concerning Pluto is the nature of his orbit. It was both highly eccentric and inclined to the ecliptic plane. Most astronomers subscribe their view, first propounded by Yamamoto in Japan in 1933. Pluto was originally a satellite of Neptune. One of the arguments put forward by Kuiper is based on Pluto's exceptionally long period of rotation of 6.4 days. This is much longer than that of any other planet except Mercury and Venus, which their slow rates of rotation predicts proximity to the Sun. As a Neptunian satellite, Pluto would undoubtedly have exhibited captured rotation, and both its rotational period and its sidereal period of revolution would have been 6.4 days. So, in this theory, Pluto was a satellite of Neptune. Some change be necessary to prevent the return of Pluto to its original character as a satellite of Neptune. If such were the case, the present almost exactly circular orbit of Triton would indeed be surprising. Kuiper and Robb, on the other hand, are both of the opinion that Pluto was released as a result of the normal loss of material from the protoplanet from which Neptune evolved. Not much is known about Neptune. Only 2 satellites are known, and has an almost exactly circular orbit. Triton, orbital radius and sidereal period, estimated period, measured. Triton is therefore larger than the Moon. Its mass has been determined the same manner as the mass of the Moon is found relative to Earth from oscillations of the parent planet about the Neptune-Triton barycenter. Mass, nearly twice the mass of the Moon. The estimated radius of Triton would be larger and the density consequently smaller than these values. The gravitational force on Triton is large enough and the temperature sufficiently low for it to have retained an atmosphere. But most of the expected gases will be frozen out. Second satellite near it. Well, that's nice. So, that would be very cold because all the heat and energy that's terrestrial, it's not from transuranic elements like uranium, is from the sun. And then secondarily, it's really as a matter of its organization and these things and how they're put together. So this is this great little book. So if that's about space technology about 40 years ago, space race, 1960s, then medieval philosophy is that and then another 800 years. So, I mean, instead of talking about like rockets, and these kind of in the ionosphere, it's a little bit more like, straw bales and maybe a good wooden cart, and a donkey or something hauling it around. In the medieval times, there was block and tackle. There was largely the survival of technology from the prior times, although there were the Dark Ages, and there were great, the Black Death, and terrible times, and economically, and also, socially, in terms of, the ravages of the Visigoths or something like that. After the fall of the Roman Empire with regards to this region of the world, because this medieval philosophy is mostly with regards to the emergence from the Dark Ages into the medieval era, the 1200s in England and centered in France. And so it's centered in the University of Paris, which is basically the oldest institution in that whole part of the world and of that sort. And so when I found this book, I was happy about it because it's from the modern library or whatever. It's got the signet of like this runner or whatever. And so I found some other good books from this imprint, and so this is from like about 1960 or something like that, and it was $2.45 in the modern library in 1964. And what it has in it, it's got Robert Grosseteste, and so Grosseteste, and he has a theory of light, and so he has a very particular theory explaining like images and flux and things like that, and its relations to matter and massy bodies and the real, vis-a-vis the images, and its nature. And then, so he starts with like a description of that for like a couple paragraphs, and then he spends like 10 pages talking about infinity and parts. And so what he gets into is like, let me talk to you about light for a second. And he's like, gives you this whole theory in about 2 or 3 paragraphs. And he says, infinity, you can put it into parts, and even in odd numbers, the asymptotic density is 1/2. It's like, oh, really? Great. I'm glad you established this in the year 1200. And he's like, this is fantastic. At the same time, you can't add them back together. They both do and don't. It's infinity. And so that's one of the greatest things about infinity, I think, is that it helps to establish that there are multiple laws of large numbers. So it's regards to the configuration energy experiment, which one of those are in effect. Classically, it's always just the classical expectations, the classical law of large numbers, classical probabilities, that a given number of dice rolls will average out to reflect that any one of the given samples will occur on an expectation on the same order as any of the other samples. There's one saying that's like, well, the expected value is they all show up the same, but they all show up about close to the same. Now, that gets in things like whether a random walk will diverge or whether it will just oscillate. And so that gets into a bunch of these different things about which laws of large numbers in effect, that whether there's any overall tendency or propensity at all, or of the restitutive and oscillating, about the attenuative and dissipative at all. All these 3 kind of ways, at least, to make it so that there's 3 laws of large numbers, at least. Here that is framed in terms of these 3 kinds of continuous domains. And then the simplest one is kind of as after this inductive set and the counting arguments and all these things that go out and into it. So Grosseteste, if I'm pronouncing that correctly, he starts explaining a theory of light, then he gets into the continua and the individua and the infinities and infinitesimals, because light as a quantity would have these properties. The very notion of this particle theory or the wave theory or anything that has that is that these thinkers were familiar with the ancient theories like the Eleatics and Democritus and Zeno and all this, of course. They had the benefits of all that came out of the Islamic Enlightenment, like Averroes and Avicenna and all this kind of stuff. And then with regards to that coming up, then a few hundred years after that was then the Mertonian school at Oxford, calculator, Bradwardine, De Continuo, or maybe they were closer in being contemporaries. I'm not quite too sure about that. This book kind of starts, about 1200. That about 1400, then we get into the Mertonian school, and only hundreds of years later, with lessons that they knew and were aware of, the Galilean, who had a great survey and pulled together a bunch of this stuff and was a popularizer and brought this and disclosed it and these kinds of things. to then 100 years later, like the Newtonian school, where Newton was a guy, and he invented and discovered some great stuff and pulled together some great stuff, while at the same time, like my favorite exposition on the formalism of real analysis, according to Newton's terms, then rather the definitions of the calculus, are Maclaurin's. So Newton was surrounded by Gregory and Maclaurin and Hooke and a bunch of other people, his giants that he stood on, as he put them. While somebody like Leibniz also independently discovered these same notions at the same time, because of course that would happen, and that shows up a lot in history, that many people, when they're working on the same subject, will sort out that they discovered the same kinds of things because they're just sitting there for the taking, and the context kind of comes together. But it helps a lot sometimes to notice, is like, well, yeah, a bunch of this stuff that would be really commonplace and trite, and in fact you should know it, and we can write it also very formally and simply in all kinds of ways today. Make it for, like, well, when we say Schnirelmann density, we mean that half of the integers are even. How exactly 0.5 or half of them. That in a sense, the multiple of one or the other, some measure aspect of their size, when you extract that relation instead of the ratio is what is between them, is 2. And so these are the kinds of things that make for that. And that's after our law of large numbers. It's like it goes to 1/2, it goes to 2, that these are the way things are. That it would be very similar and familiar to 800 years ago. These people, they've so written out exactly that they say the same things. But it's to be said then that it's as well that Schnirelmann put this together in the latest, greatest, so far generalization of all time, because mathematics should always kind of grow out that way. And so it gets into wider and wider fields, vis-a-vis smaller and smaller fields. It's like, well, I made the definition in our smaller field. It's like our opinion or our principal branch, or this is the way things are in our smaller subfield, and that's how it is. It's like, well, that's fine, that's great. So in a sense, when we say Schnirelmann density, who was a tragic fellow of character, he was a young man, he was a stalwart and earnest kind of guy, and numer theorist, but he was kind of awkward, and then he died young, and tragically, like in his 20s or something like that. But he's romantic for some reason, and so he's also held up as kind of a school of a man or something like that somehow. Because otherwise we just call it asymptotic density today, but you can also say it's just plain old medieval mathematics of infinity in the aliquot parts. It's aliquot, A-L-I-Q-U-O-T, aliquot parts, that these are the kinds of things that then we just call it density. It's the density of these things. So that really amused me to start reading about. And here's this John Scotus Eriganus. So before Duns Scotus, who was like, infinity is in the numbers. Infinity is in. And he had the great approbation of the church, and he had all this other stuff going on, and he was really a kind guy. And it was really, he had a philosophy, besides also bringing strongly the Platonic and the Augustinian. Kind of sits next to Thomas Aquinas, which is much more like, I'm Socratic and I'm Aristotelian, and so don't ask me about Plato because we're going to work it out this way, And Anachim, he was just like, let's keep things simple, and it's like, you can't see what I'm doing, right? There you go. See? Nothing to see here. William of Ockham or whatever, that when it's like Sherlock Holmes' means of deduction is like, when everything else is eliminated, however improbable it is, it's the thing, or whatever. That Duns Scotus and Aquinas and William of Ockham represent these three kinds of contrasting views. And we can say it's kind of like Salviati and Sangredo or whatever, or Socrates and Plato and Aristotle sometimes, or the Eleatics and Parmenides, Heraclitus, and and I don't know who'd be the third and that kind of stuff. But in these medieval times, so this Aragonu, who's an Irishman, and so he's like, this is the greatest thinker of the year 900 or something like that. And he was around, and so that is like, then after him it was like there's Roger Bacon, and so Bacon was like this friar, and he was he was very well studied, and he's very scientific. So a lot of the great concepts that are profound, the scientific sort, can be arrived at from these medieval philosophies, while at the same time, what's so great is that modernly today, we can extract from the lens through their experiences and what is the essence of those things. We can turn these things over in our minds, and as well in terms of our current contexts. And then up to like Bernard d'Espagnat's on physics and philosophy is like, hey, the wave equation is real. How do we think it? So that's definitely something that I'd like to understand and discover some more. Well, that's Moment in Motion today. So what I'd wanted to talk about was some more about this Zeno's continuum, and what it means is from the last talk. So I'll think about this a little bit more and kind of review that a bit, because it's framed is what we discussed here, and this is running a bit long, but is framed in terms of the idea of the operator calculus and finding these invariants, and then what the implicits go to get implied, these functions that make the invariants like so. And everybody knows the exponential is its own antiderivative, but the equivalency function is also, it's not really going anywhere, you know. Hey, have a great day.